Okay, so good evening, everyone. So let's continue our previous lecture on the audio compressions. So, okay, so we have learned several things, in general for the audio compressions. First of all, we know that uh, in terms of audio, we are actually, the main interactive person would be human being. So we will trying to do everything. No matter the compressions, the processing, the main target would be for human being. Okay, this is not meant for uh, machines and also not meant for any computer for processing purposes, but for human being daily basis interactions. Okay, so in previous lecture we learned about the frequency masking, and now we will learn about the temporal masking. So we have two types of masking here. The first one will be the frequency masking. The second one will be the temporal masking. So frequency masking would be specifically referring to how how a very significant frequency can mask those frequency which is insignificance and which is just adjacent to the significance uh, frequency. So you have a frequency which is very significant, for example, a loud noise, a loud, noise from maybe a boom, and then the rest of the frequency which is not so significant would be masked out by frequency. So in this phenomenon, we know this as a frequency masking. So if let's say you have another signal coming in, which is higher than, exceed the masking level. So this signal would be able to perceived by human being. Okay, so temporal masking is something similar but a bit different. Is that the frequency masking is emphasized on the frequency, but for temporal masking, it is emphasized on the time domain. Okay, so after a dance, exposed to a very loud noise, usually it takes quite a time for our hearing to return to normal. So this is what I have gave example in this condition where you attend maybe go to a concert and or don't go to a sort of bar, and then after you exit from the concert, perhaps it's very difficult for you. It's very difficult for you to perhaps it's very difficult for you to and hear whatever people whispering to you because because the signal level is too low. Okay, so generally any loud tone cause the hearing receptor in the ear little hair-like structure called cilia to be saturated, and they require time to recover. Okay, so this is the reason why human being cannot expose to continuous exposed to a noise for a very short period of time, because even though you keep on exposure to the specific uh, signal or the noise or the sound from the ambient environment, the cilia is already saturated and it will not generate anything or any signal to our brain. So that is why we hear nothing at that moment. So to quantify this type of behavior, we can measure the time sensitivity of hearing by another masking experiment. So temporal masking occurs when two sounds appear within a small interval of time. So always remember when we deal with, when we use the words temporal, we are always talking in terms of time domain. When we talk about the spatial, it is about spaces, and when we talk about frequency, it is about the frequency. Okay, so a stronger sound may mask weaker one, even if the masking precedes the masker pre or post masking. Okay, so for this one, let's say you have for example you have a very high frequency sound here or very big noise here, and you have a music playing. Okay, so the music is literally play before this noise occur. So eventually when the music play first, this is quite logic. I believe you all this is sort of logic phenomenon. For example, you're playing your music in the room, very soft music like those jazz music. Then suddenly, neighbor doing construction, drilling the wall and etc. So no matter, even though your music is playing before the noise, when the noise occur at this moment, so it will mask up the entire soft jazz music that you are playing in your room. Okay, so this is what meant by pre or post processing. Sorry, pre or post masking. Post masking would be whenever your neighbor already drilling the wall, so you just about to start to play the music, but you cannot hear any because the music is, I mean, the tone is too soft and it's being masked out by the construction noise. Okay, so this is what meant by pre and post. Okay, so the louder the test tone, the shorter it takes for the test tone to be here once the masking tool is removed. Okay, so which means when you expose, when someone yell at your ear, you might suffer from a very short time of humming effect where you cannot hear some other things where it, I mean, in that specific very short period of time. But that your cilia would eventually recover maybe after 1 minute. But if let's say you are, I mean, just pass by somewhere and there is sort of a boom occur because the boom sound, the noise is too high, and it will eventually saturate, causing the cilia to be saturated for more than maybe 5 to 30 seconds. Sorry, 5 minutes to 30 minutes. So that is what it mean by this one. The louder the test time, the test tone, the shorter it takes for the test tone to be here. Okay. So the phenomena of saturations also depends on how long the masking tone has been applied. So if a masking tone is played longer, it takes longer before a test tone can be heard. Okay. So this is what I mentioned just now. Which means you are exposing to high level of noise for a long period of time. I think in the OSHA Act, Occupational Safety and Health Regulate, or OSHA, 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 Occupational Safety and Health Act, also 1994. So that one, in that particular act, it did mention, I mean, there is an act to guide, I mean, the employer to provide a safe workplace for the employee. Okay, so for those that working in electronics may not, I mean, specifically understand or address or be being protected by this act. But nonetheless, for those that working in construction area or maybe sort of closed room with which require him to expose to high level of noise for a long period of time, there is an act to protect this or this employee, so that you can only expose to a specific limit of noise for I think it's 20 to 25 minutes, and then later on you need to rest for another 30 minutes and then continue your task. Okay, so the reason why is that if you expose to the noise for a long period of time, it tends to, I mean, injure or jeopardize the internal organ. The first one would be the, I mean, directly would be the cilia, the eardrum, and etc. Okay, so temporal, so that is I mean that is all about the temporal masking. So again, let us recall frequency masking and temporal masking share very, I mean, a lot of similarity. Just that frequency masking is meant to focus in frequency. Okay, where your x-axis is always about the frequency, and for temporal masking it is about time domain. Okay, so your x-axis would be always the second or time, any maybe minutes or hours lah. But it's rare to have minutes or hours. Usually it's I mean the unit for time is second. So Mpeg audio compressions. So as we learned before, the Mpeg is a group of expert group which is more on the motion picture. Okay, and JPEG would be the static picture or static graphic. Okay, have you ever attended a dance and found that for quite some time afterwards you couldn't hear much, you were dealing with a type of temporal masking. Okay, so which means you're exposed to a high level of noise, and once after you exposed to that particular noise, and then someone whispered to you, it's hardly for you to accept or receive the message from your friend or someone else. That is because the cilia is being saturated, and the frequency, the resonance of the patterns of the vibrations cannot pick up by your eardrum or the cilia. In some cases, if a very loud tone is produced, you also notice that it's impossible to hear any sound nearby in the frequency spectrum. For example, the band singing may be drawn out by the lead guitar. If you notice this, you have experienced frequency. Why this is, I mean, uh, this why we, I mean, why this example is considered as frequency is that I hope you all still remember the Fletcher-Munson graph. Is that the lead guitar or the electronic guitar is actually uh, play at the frequency where it is most sensitive to human being. Okay, so that is why it is like doing writing an essay, and suddenly there is some highlight over there. So the highlight would automatically draw our attention towards that part. So the same happens here, where the frequency which will able to draw or prioritize for human being would be the frequency, I think between 50 and 5 and 50 kilohertz. So that is why whenever frequency which is much more sensitive to human being is played at the same time when other sound or tone is being played, that would be automatic draw your attention towards that particular frequency. So this is so-called the frequency masking. Okay, and also the frequency masking must be determined. Must be studied along with the amplitude. If let's say uh, a very soft tone is being played at a speed frequency which is very sensitive by human, but the amplitude or the intensity of the music or audio is very very soft, so it is unlikely to cause a frequency masking. Okay, so Mpeg audio use this kind of perception phenomenon by simply giving out on the tone that can't be heard anyway. This is so-called the perception. Uh, compression in terms of perceptual, human perceptual, whereby no matter this kind of frequency, it's appear on being omits from the data, you will, as a human, will unable to listen as well. So, but nonetheless, all this data, all not, not only particular this data, but all the data which present in the file, no matter audio file or image file, will cause or will take up size or spaces. Okay, so that is why since we have limited bandwidth, always remember the reason why we need to perform compression is that we have limited bandwidth and we have limited storage. Okay, so that is the reason why we need to perform compression, no matter for image or audio, it is still the same. Okay, so since we have a very limited bandwidth and also limited storage size, so it is rational for us to remove this kind of data from the image or audio itself, in order to preserve to save up the storage space or save up the to reduce the time taken to transfer the audio file or the image through a specific bandwidth. So Mpeg audio codec makes decision on when and to what degree frequency masking and temporal masking make some component of music inaudible. So basically, Mpeg audio codec is sort of algorithms which make decision on when you want to omit the data and to what degree you want to omit the data. Okay, for example, I want to omit the data at 5 seconds, but how much of data you want to remove. So that would be decided by the Mpeg audio codec. So this is the general format. this is the general format of the encoder and decoder, where A is encoder, B is decoder. So, basically, the encoder, I mean, to encode or to compress the audio, usually is very quite complex, but the decoder usually is very simple. Nonetheless, uh, this is only the this figure A this figure A is the general uh, block diagram for the audio compression, which means because in Mpeg you have Mpeg 1, Mpeg 2, and Mpeg 3, which is Mpeg layer 1, layer 2, and layer 3. In short, we usually call it as Mpeg 1, Mpeg 2, or Mpeg 3. Okay, so these are, I mean, for A, this is the general flow or general function in each of the audio compression. Nonetheless, when you go for, I mean, when later on I show you all the Mpeg layer 1, Mpeg layer 2, the appearance or the arrangement of block diagram will be different from this one. And ones can always cater or improve the compressions block diagram. But nonetheless, you will still have all these kind of basic functions here lah. It is just like when you are when you are performing I mean doing image analysis or image processing. It is always start with input image and then pre-processing, segmentation, feature extraction, classification, and sometimes you need post-processing after segmentation, something like that. This is always the general flow of the image processing, but nonetheless, it is not the fixed flow in image processing. For example, if your input image is very good, I mean, every all the contrast is good, the features can be clearly visible, so you don't need any pre-processing. But if let's say you have after you perform the segmentation or maybe classification or any other possible method to identify the region of interest, after you're getting the region of interest, perhaps the result is very perfect, so you don't need any post-processing. And if let's say you don't need to partition the object of interest into different clusters, so you don't need feature extraction and classification. But nonetheless, in general terms, we will still mention this as part of the image processing flow. Okay, so it is the same here, whereby this will be the general flow of the audio processing. Sorry, audio compression. So first of all, you have a time to frequency transformation. So which means you need to transfer the data from time domain to frequency domain. And then at the same time, I mean, this is from PZM. After you receive the data from PZM, I hope you all still can recall. PZM is actually, I mean, to perform analog to digital conversions. And after the conversion, it will, the output of PZM will be binary, like 1 and 0, 1 and 0. So after you getting the result from PCM, it will directly input to this block where you need to perform time to frequency domain transformation. And at the same time, the data here will be transferred to the psychoacoustic modeling. Okay, psychoacoustic modeling would be the main block. I mean, the main function of psychoacoustic modeling would be to perform frequency masking, temporal masking, or some other sophisticated masking algorithm. Okay, we will perform everything here. And then later on, both of these data join together, and in this block, you need to determine what to drop, which means you have your time to frequency domain. For example, you get your time to frequency domain. For example, you have uh, 10 apple, but all these 10 apple is in analog, so you convert to digital, 10 digital apple. Okay, so in here, you will decide which apple, what features of the apple to remove. Okay, then later on, from this 10 digital apple, you will apply the message get from the psychoacoustic model to eliminate part of the apple. So later on, you will get maybe 5 apple left, 5 digital apple. And then these 5 digital apple will be include in the bitstream formatting and become something 1010. Okay, so this is the general flow of the Mpeg audio compression. Okay, Mpeg audio compression takes an advantage of psychoacoustic model. As I mentioned previously, the energy in terms of sound wave would be known as acoustic energy, and psychoacoustic would be combination of human, the psychological human, and also the acoustic. Okay, so psychoacoustic model would be referring to frequency masking, temporal masking, and also some other complicated or sophisticated masks. So construct a large multi-dimensional lookup table to transmit mass frequency component using fewer bit. Mpeg audio overview applies a filter bank to the input to break it into frequency component. And in parallel, psychoacoustic is applied to the data for bit allocation block. The number of bit allocated are used to quantize the info from the filter bank, providing the compression. So this is the first block here, which is referring to this one. You transfer to time frequency domain, and in parallel, which means at the same time, you have a psychoacoustic, and then both of these will form together and perform bit allocations. Okay. Mpeg audio offer three compatible layer, which is Mpeg layer 1, layer 2, and layer 3. And each succeeding level are able to understand the lower layer. Each succeeding layer offer more complexity in terms of in the psychoacoustic model and better compression for a high level of audio quality. So which means you have three different layer 1, layer 2, and layer 3. Or I should put it in this such a way, layer 1, layer 2, and layer 3. Okay, which means layer 1 is actually a subset of layer 2, which means in layer 2 you will able to perform you will perform all the algorithm in layer 1, and then you add in some other in layer 2. And for layer 3, you will perform all the algorithm in layer 2, and you add in some other for layer 3. Okay, but nonetheless, but of course, if you are requesting higher and higher level, I mean layer, you would get a better data. For example, you were able to get clearer. I mean, after the compressions, you were able to get a small size, of course, but with a clearer or higher quality of data. Okay, so for sure it will be layer 3 lah. But nonetheless, layer 3 will have more, I mean, more size as compared to layer 1 and layer 2. Okay, so you need to consider the trade-off lah. Okay. So each succeeding layer will increase compression's effectiveness accompanied by extra delay, which mean when you have which mean the time taken to perform Mpeg compression like using layer 1, layer 2, and layer 3, the time taken will be increased. This has lesser time, this require more time. The objective of Mpeg layer is to provide a good trade-off between quality and bitrate. Bitrate is actually referring to the size. So you have to consider the trade-off here, whereby you want to prioritize the bit rate or you want to prioritize the quality. Okay, layer 1, layer 2, and layer 3. Layer 1 quality can be quite good, providing a comparative high bit rate is available. Digital audio tape usually use layer 1 at around 192 kbps. And layer 2 has more complexity. Layer 2 was proposed for use in digital audio broadcasting, and layer 3, which is the MP3, is the most complex and was originally aimed at audio transmission over ISDN line. Okay, so I think you all know about MP3, right? Eventually, last time we have sort of, you know, the digital player, sort of digital mini something like iPod. We call it as MP3 lah, but MP3 actually referring to Mpeg layer 3. Okay, instead of MP3. But of course, MP3 is also an extension. For example, your name and .mp3. But MP3 is only include the audio, which means there is no images. So if let's say you have MP3 and someone said that this is a video, it's not possible lah, because MP3 is only applicable for audio. If you want to include images, which means it is a video. So for sure it is MP4. So most of the complexity increase is at the encoder, not decoder. Okay, that is because encoder is the one who encode or perform the compressions, and it has three different layers, which is layer 1, 2, and 3. Okay, with increasing layer, you will increase the complexity of the algorithm, but the decoder will remain the same, whereby you just need to decode the uh, data where you receive. So Mpeg approach compressions rely on these two quantizations and take advantage of human auditory system. Human cannot differentiate the sound within a critical band. So this is, as I mentioned in the last lecture, critical band is a band whereby human being able to listen. So critical band is sort of band where someone able to listen something. So if let's say there is another frequency or another noise coming in to your specific band wave, specific critical band, and interrupt your critical band using higher frequency. So which means this will mask out the rest of the area. Okay, so this is so called this is so called the frequency masking. Okay, so now we look into some of the main function of each of these block. But nonetheless, again, this is not, MPEG 1, MPEG 2, and MPEG 3 has their very own, block diagram. So this is the general or the basic MPEG audio encoder, which means this is not MPEG 1, MPEG layer 1, layer 2, or layer 3. Okay, this is none from this, but this would be the basic or the fundamental function block which will appear in all these layer 1, layer 2, and layer 3. Okay, I will show you all the Mpeg layer 1, layer 2, and layer 3 encoder later on. Okay, but now we only discuss some of the basic functions in this block diagram. Okay, so we already explained PCM, whereby you have your analog data, analog sinusoidal wave, and then convert to digital by perform sampling and quantization. Sampling is in terms of time domain, and quantization is in terms of amplitude or frequency. So later on perform this one, you will need to convert, binarize it to become 1 and 0. So from here, you will need to the output from PCM, you will need to use this output to and supply it to this one time to frequency domain and also the psychoacoustic model. So Mpeg encoder employ a bank of filter to analyze the frequency, which is the spectrum component of the audio signal by calculating a frequency transform of a window of signal value. So decomposes the signal into subbands. There are 32 subbands. Layer 1 and Layer 2 codec implement a quadrature mirror filter bank, whereas Layer 3 codec adds discrete DCT, discrete cosine transform, and psychoacoustic model, which is the Fourier transform. So the algorithm, so as you can see, layer 1 and layer 2, they only use this method, this filter bank, but for layer 3, it adds on another, which means it is using this one, but add on the DCT and also the Fourier transform. So the algorithm proceed by dividing the input into 32 frequency subband using filter bank. This is the algorithm will partitions or divide or characterize the input into 32 frequency. So this 32 frequency actually 0 to 31. Okay, 32 subband. A linear operation taking 32 PCM sample and sample in time domain, and the output is 32 frequency coefficient. In layer 1 encoder, the sets of 32 PCM are first assembly into a set of 12 group of 32 subband. This can refer to this one. Okay. An inherent time lag in decoder equal to the time accumulate, which is this one. Because first of all, you will this is the input signal. So from the input signal, you will partition into 32 subband. So for each subband, you will get 12 sample. Okay, this is for layer 1. If for layer 2 and layer 3, you will get 36 sample instead. Okay, so this is to illustrate the time to frequency transformations. As mentioned before, this is the output from PCM, and the output from PCM would be partitions into 32 subband. Okay, starting from 0 to 31, and for each subband, you will generate 12 sample because we need to take the sample, right. This is to transfer from time domain to frequency domain, so you need to perform the sampling. Okay, so in order to perform the sampling, you get 12 sample for layer 1, but for layer 2 and layer 3, you will get 36 sample. Okay, not only 12. So figure shows how samples are organized. Layer 2 and layer 3 are actually accumulate more than 12 samples for each subband. A frame consists of 1152. How to get this is that you have uh, 12 sample, 12 sample, and 12 sample multiplied by 32 subband. So you will get 1152. Okay. Uh, for layer 1, you only have 12 samples for each subband, but for layer 2 and 3, you have 36. Okay, so that is all for the time to frequency transformations. And for psychoacoustic, we will perform the frequency masking, temporal masking, and some other filter bank. Frequency masking by psychoacoustic model to estimate the just noticeable noise level. Encoder balance the masking. Encoder balance the masking behavior and available number of bit by discarding inaudible frequency. Scaling quantizations according to the sound level that is left over above masking level. So the main purpose of the psychoacoustic is to implement the frequency masking and temporal masking to omit some of the, so-called redundancy informations. Why it is so-called the redundancy is that eventually the data presence in your audio or image, once you're no longer or unable to understand or perceive the message, that is because the message is just inaudible because it is already masked out by either frequency or the temporal. So may take into account the actual width of the critical band. For practical purpose, audible frequency are divided into 24 main critical band. To keep simplicity, adopt a uniform width for each currency analysis filter using the two overlapping sub band. So this, at this, at the psychoacoustic model, we will also determine the audible frequency. As I mentioned just now, we have specific range or so-called the critical band, which human can understand or hear something, I would say. But if so-called, if some of the frequencies fall within the critical band, so these are critical band, fall within the critical band, so it is inaudible to human. Okay, since all this data is inaudible to human, it is kind of useless to retain this data in uh, the audio file or in the audio file. So in the psychoacoustic model, the algorithm will also search for this kind of data and omit it. So this is the psychoacoustic model. Layer 1, the psychoacoustic model use only frequency masking with a bit rates of around 32 kbps and 448 kbps for stereo. And layer 2, another psychoacoustic model is adopted, which is temporal masking. This is done by accumulating more sample and examining the temporal masking between the current block of the sample and the one just before and just after. Okay, which means you compare it with the uh, succeeding and preceding blocks. So bit rates 32 to 192 kbps mono and for the 64 to 384 kbps for stereo. Okay, basically stereo would be double up, multiplied by 2. Okay, so because stereo is two different signal, right? So for layer 3, lower bit is applied by using more sophisticated subband analysis with non-uniform subband width. Also, non-uniform subband width, which means the subband is not a fixed form interval. Okay. Also, non-uniform condensation and entropy coding, which is the Huffman coding with a bit rate of 32 to 320 kbps used. Okay. So, which means, as I mentioned just now, this is layer 1, this is layer 2, and this is layer 3. So which means layer 3 is not only doing this only, but cover all this. Okay, and layer 2 is not using the temporal masking only, but also frequency masking. But layer 1 only apply the frequency masking. Okay, so this is so-called, level 1, layer 1, layer 2, and layer 3. That is why, because more sophisticated filter bank is being used in higher level. That is why the higher level would be expected to have higher quality, and at the same time it will have, it will require more spaces lah. Okay, bit rate, bit allocation, quantizing and coding. This is to decide what to drop and what to remain. The bit allocation algorithm is not the core of the Mpeg compression. It can be done in multiple possible ways. Basically, in Mpeg compressions, these two are the core. Okay, this is not the core. It can be it can it can be done in multiple possible ways. The main purpose of bit allocation algorithm is to ensure that all the quantization noise is below the masking threshold. Quantization noise is something that we don't want to have. Of course, it is inevitable. Just that we try to mask up this one. For example, the masking threshold is, let's say, this is the masking threshold. Okay. Uh, uh, let's say this is the masking threshold. So this is the quantization noise. Okay. So if let's say your quantization noise is higher than the masking threshold, for example, this is the masking threshold. Sorry, this is the quantization noise, and this is the masking threshold. So for this area, it may introduce disturbance or some artifacts to your audio file. Okay, so that is why in bit allocation algorithm, we try to ensure that the masking threshold is greater than the quantization noise. Okay, so since it is under the masking threshold, so all this noise will be masked out. When this noise is being masked out, which means this noise will not create any disturbance or any artifacts or introduce any artifacts into your audio file. Okay, so that is one of the function of this bit allocation algorithm. This is to ensure the quantization noise, which can produce distortions, is inaudible to human. Okay, as I mentioned before, is in we cannot really omit or exclude all the quantization noise, because some quantization is uh very soft and very minimal. So if you want to omit that part of noise, sometimes you may omit some of the important noise, which sort of whispering. You might remove all those kind of noise, all those kind of message. So by doing this bit allocation algorithm, we will able to ensure that the quantization noise is not audible to human. So a common scheme is used. Nonetheless, this is just a common scheme, because there are a lot of different types of allocation algorithms or approaches out there. This is only the common one. Okay, for example, if you want to come from your home to Tai, you see, perhaps you will drive. Okay, but nonetheless, drive is not the only way to come to Tai. You see, you want to cycle, walk, grab, motor, and whatsoever also can. But the most common one would be drive lah. Okay, so each subband, the psychoacoustic model calculate the SMR, okay, in dB, and then the mass to noise ratio MNR is defined as below. So MNR is actually SNR minus my SMR. Okay, this is mass. So the lowest MNR, which means the lowest value in terms of dB for NMR, is determined, and the number of code bit allocation to this band subband is increased, which means you first of all you get the lowest NMR. Second, you allocate more bit rate to this specific signal, so that when the signal has more bit rate, so you were able to increase the signal to noise ratio. So recall back, signal to noise ratio, the higher the better. If signal to noise ratio is very less or 1 to 1, if 1 to 1, which means your noise is 50% and your useful signal is 50% as well. Which when you have signal to noise ratio lower than 1 to 1 ratio, which means you have more noise than the signal. Okay, so that is why we always want to have high ratio or high number of SNR. Okay, so first of all, you get your SNR and you get your SMR, and then SNR minus SMR, you will get MNR. So first of all, you get the value, identify which is the lowest MNR, and then increase the bit rate of that specific NMR. So with a new bit, with a new bit allocation, the SNR of the subband or the subband with previously lowest MNR is increased, as the SNR is proportional to the number of allocation bit. Thus, the MNR of the subband is increased as well, which means the current lowest MNR, after getting extra bit from the algorithm, it is no longer the lowest. Some other signal would be the lowest now. So thus the MNR of the subband is increased as well. The algorithm then search again for the next subband with the lowest MNR. This progress is iterates until there are no more bit available to allocate. The main purpose of this entire process is to allocate more bit rate or allocate more bits to useful information rather than those with lower SNR. Okay, uh, let me put it like this. So higher SNR, which means the signal is very strong or the value is very good lah. Okay, which means you have high SNR. So after you get this one to minus this one, you will get low MNR. So for those that has lowest MNR, which means this signal or this this audio signal is useful, which means it is audible to human being. But nonetheless, it has the lowest bit rate at this moment. So that is why the algorithm will then allocate extra bit to this specific, lowest MNR. So after the lowest MNR, the current lowest MNR get the extra bit, it will increase its SNR. Since the SNR is increased, which means you can have more, we can allocate more space for this data to describe himself. Okay, so next you will search for the next lowest NMR. So always remember the MNR is those signal which is audible to human and it is useful. Okay, so this kind of allocation keep on iterate until your the number of bit available is being all used up. For example, I have 100, so I want to buy something useful. So I will keep on buying something useful until my 100 being used up. Okay, so this is the logic behind the bit allocations algorithm. So at the end of the algorithm, bit allocation algorithm allow more bits for subband that is meaningful to human, which means it's audible by human. We don't really know the content of the information. For example, when you try to speak, when you try to speak, the first 5 seconds is talk something irrelevant, but then later on, starting from the 10 second, the information is very crucial. but the algorithm did not know which part of the algorithm, I mean, which part of the audio carry an important, I mean, carry important message. But nonetheless, the algorithm can only determine if this specific tone is audible to human. If it is audible to human and it is not, I mean, masked up by any frequency masking or temporal masking, so it is considered meaningful. Okay, the meaningful here, which means it is able to be understood by human being, not the message itself is meaningful. Okay, so do not misunderstand the terms meaningful here. So at the end of the algorithm, the bit allocations algorithm allocate more bit for subband that is meaningful to human, which can be perceived by human as determined by the psychoacoustic model, and less bit for subband that is not important and difficult to be perceived by human. Which means if let's say, mm, if let's say I have this value and I will try to allocate more bit to the to those signal which is easier for human being to understand. Okay, and the rest which is under the frequency masking or near to the frequency masking, or eventually the frequency is lower than the audible frequency, or maybe higher than the audible frequency. So this level of noise of signal will be allocated by lower bit. Okay, and those which is meaningful, which carry meaningful which is meaningful the audio which is meaningful to human being would be able to allocate more bit to describe the audio itself. Okay, okay, any questions until now for bit, I mean the general flow of this? No. Okay, so again, let me recap everything. First of all, you have your analog signal, you convert to digital, and then binarize it to become 1010. And then later on, this set of the output will be submit, I mean, will be proceed to time to frequency transformation. And then at here is mainly to transform to frequency. So you need to perform sampling. You will get 32 subband. At each subband, you will get 12 sample. This 12 sample is for L1, layer 1, and for layer 2 and layer 3, you get 36 sample. Okay, so at the same time, parallelly, you will get, I mean, this data will be input to psychoacoustic model. In psychoacoustic model, layer 1 would be using, I mean, determine which part is being masked out by the frequency masking. Layer 2 would be add on temporal plus frequency, and layer 3, these two plus some other sophisticated filter. The reason why I did not mention what types filter is it because there are too many types of filter, and yeah, and again the psychoacoustic model is the most complicated part in audio compressions. So uh, I don't think we need to study until that part lah. Okay, that is more on audio processing, which is very in depth. Okay, so for this one, for our syllabus, we just need to know what is psychoacoustic model and what actually psychoacoustic model doing. And for each of the level, layer, sorry, now each of the layer, what would be the function of this different layer and what would be the difference. So later on in bit, from the message from carry, output from the psychoacoustic model and the time to frequency domain is combined to determine what types of signal or what types of frequency should be dropped. Okay, because in bit allocation and quantization encoding, you have to select what to drop. Okay, and then after you select what to drop, the remaining one will be convert to bit stream formatting. Okay, so in bits allocation algorithm, it is not the core of the video, of the audio process compressions, but nonetheless, it is part of it, okay, but not the core, of course. The core would be psychoacoustic and time to frequency transformation. So for this one, you have a different kind of algorithm to do so, but the main idea is that you want to allocate more bit to meaningful data, and you try to allocate lesser bit or none to those signal which is not so audible by human. Okay, so this is the main idea or the main functions of these bit allocations and quantization and coding blocks. Okay. So this is the as I mentioned just now, this is not the this is not the not even this is only a general block, which means uh, a general flow or general block diagram of the Mpeg processing, Mpeg video audio compression, but it is not exactly either the layer one, layer two, nor layer three. Okay. So this is Mpeg audio layer one and layer two. As you can see, the block diagram is a bit different. Okay, the block diagram is a bit different, and some point, the it will mention the specific algorithm being used. For example, you have 32 subband. This is time to frequency domain transformation, and you have FFT, fast Fourier transform, and you input to psychoacoustic model, linear quantizer, and then site information coding and bitstream formatting and get your code. Basically, these are some part which has been mentioned by the general block diagram. This is time to frequency domain transformation. This is a psychoacoustic model, and this somewhat is see as a pre-processing before you input to psychoacoustic model. uh, this is the bit stream, and this would be this and this these two would be see as bit allocations. Okay, and later on output lah. So Mpeg audio layer one and layer two, mask calculation are performed. Mask calculation are performed in parallel with subband filtering. The mask curve uh, calculations require an accurate frequency decomposition in the signal using DFT. And then in layer one, 16 uniform quantizer are pre-calculated. The index of the quantizer is sent as 4 bit of site information for each subband. The maximum resolution of each quantizer is 15 bit. And for layer two, the main difference with the layer one is that there are three groups of 12 sample. I hope you still can recall in time to frequency domain, you have 32 subband, right? So after the subband, 32 subband, for layer one, you will get 12 sample. For layer two and three, you will get 36, which means another three groups of 12 samples add up become 36. So three groups of 12 samples are encoded in each frame, and temporal masking is brought into play. Okay, this is the difference, which means you have not only the frequency masking, but temporal masking as well as the frequency masking. So note that layer one only use 12 sample and layer one only use frequency masking. The psychoacoustic model does better at modeling slowly changing sound if the time window is used is longer. Bit allocation is applied to window length of 36 sample instead of 12, but bit allocation for layer 1 is only 12. Okay. The resolution of quantizer is increased from 15 to 16, 15 bit to 16 bit. So the main advantage is that a single scaling factor can be used for all three groups before current and next. Okay, so this would be some of the highlights between the differences, with layer one, whereby in terms of time to frequency domain, you have 32 subband, uh, 32 subband, yeah, both also have 32 subband, just that you get three groups of 12 sample, but in layer one, you only have one group, which is 12 sample alone for each subband. And in psychoacoustic model, layer one only use the frequency masking, but for layer two, you have frequency and temporal masking. Okay, and the resolution of quantizer is 15 bits for layer one, 16 bit for layer two. So this is another, the example for layer three, Mpeg audio layer three. As you can observe, it has I mean, complicated, I mean, not complicated, but more comprehensive or complex uh, block diagram. So first of all, you will put it into 32 subband, and then you perform fast Fourier transform, M, MDCT, psychoacoustic model, non-uniform quantization, self-information coding, and then you also use Huffman coding and bitstream formatting and get your result. Okay. But nonetheless, you don't, I mean, don't worry on this one. We will not ask in very details. I mean, if let's say it's appeared in your examination, all this will not ask in detail. Don't worry. I don't think we will ask something beyond what is included in your syllabus and what is included in in the the lecture notes. Of course, you don't expect something. I mean similar from the lecture notes that, for example, you don't expect something that you can memorize and then you just open up the test paper and you can write everything, just like eating up the entire lecture notes. Not something like that. As I mentioned, I always want to test the logic or the logic or the idea behind the MTAA. For example, uh, I will give you an example, and then I hope you all can correlate with the fundamental that we learn here. Okay, I I will ask about the knowledge level, but not really. I mean, uh, a lot of marks a day lah. Okay, because I think for senior year in engineering, it's better for you all to train up how to think logically, justify, yeah, but not to memorize. If memorizations, the way like your calculations, all those should be in junior year or mid junior lah. Okay. So Mpeg audio layer three, as I mentioned before, this is layer one, this is layer two, and this is layer three. Okay, which means the layer three will be very comprehensive and inclusive everything in layer two and layer one. Okay, Mpeg layer three use a bit rate similar to layer one and layer two, but the procedure substantially better audio quality. Again, the price of increased complexity. This is normal lah. Okay, whenever you use a simple algorithms, it is always, I mean, not always lah, but most of the time the result is not so promising. But when you have a better, I mean, more sophisticated algorithm or more complex algorithm, you would able to see that the result or the quality of the output is better, and because you address more and more different uncertainty or the factor which is appear in your input data. Okay, so this layer also take into account stereo redundancy, which means if you have uh, signal from two different stereo, because stereo is meant to have signal one and signal two, right? So these two signal are some to some extent it is isolated. So this layer also take into account for this kind of data. If it is, appear here and appear here, for example, the signal at this, let's take an example that the signal from your left earpiece or the right earpiece. So if let's say the signal both are carrying the message that something appear in front of you. So for this kind of message, it is shared between left and right earpiece. So you can actually remove part of it. I mean, either left or right. So you will still able to understand this one. I mean, there are something coming in front of you because of the audio localization, right? Because when the sound appear at the right hand side, you would think that something is coming from the right side. When the sound is appear from your left earpiece, you would think that something from coming to you at your left hand side. And if both of these both the amplitude is remain the same, you will find that something is coming in front of you. Okay, so for this kind of redundancy, so somewhat you can actually remove part of it to save up more bit and also more space for that one. It also use a refinement of Fourier transform. Let me Refinement of Fourier transform, which is the modified DCT, which address the problem of DCT at boundary of the window use. Okay, so it is, I mean, it use the layer 3 actually use a better DCT function, which is an improved method of DCT, and address this issue whereby the boundary of the windows, which occur at the boundary of the window. The quantized value is coded using Huffman coding, a specific method for entropy coding, and the Huffman coding is lossless method. Okay, so that is the difference. You don't need to memorize this one. Okay, you don't need to memorize this one, and also uh this one. Okay, but you need to know the basic block diagram, which is this one. Okay, you have to know the basic flow, the basic flow for the audio processing. What is the general block or the general flow involved in the audio compressions? Okay, and this is eventually can evolve to become layer 1, layer 2, and layer 3. Okay, so any questions so far before we go into next subsection? No? Okay. If no, then we take 5 and then we will continue to next subsections. All right. Okay. Let's continue. Okay, let's continue. The audio format. So the remaining of this chapter is to is to mention some of the audio format that yeah. All audio format fall within these three major category: uncompressed audio format, lossy, and lossless. Okay. This is the level of the level of format is the same as in image. Okay. Uncompressed, lossy, and lossless. Uncompressed, which means there is no none of the compression algorithm is being implemented in this audio all this data lah. Okay, Lucy would be once you compress it, you will not able to recover all those lost data, and lossless would be those that you can recover back later on. Okay. Once you know which category you want, all you have to do is pick the format within that category that best suits your need. Okay. Again, MTAA multimedias is always dependence on the application. Okay. There is no such best algorithm for this and that. There is no best extension of format for image or for audio. It is always depends on your applications. Okay. So, first of all, you need to identify which format you want at the end of the day. You want it to be loosey, lossless, or uncompressed. So, if let's say you want to get lossless compressed audio, whereby all the omitted data is not so important and can be ignored. So you can select any of the any of the extension under this category. So these are some of the category, of course not all, but some of the category in these three formats: uncompressed, lossy, and lossless. So which is WAV, AIFF, MP3, and all these three. So Vobis is most commonly used in conjunction with the OGG container format, and it is therefore often referred as OGG Vobis. Vobis is a continuer of audio compression development started in 1993 by Chris Montgomery. Note for WMA, a lossless connect WMA lossless compress audio data without loss of audio fidelity. Nevertheless, the regular WMA format is lossy. Okay, different types. So digital audio format, this is just the extension, and codec is the algorithm. Codec is the algorithm used in this extension. So this is using PCM, Mpeg audio layer 3, which is MP3 lah. Okay, I believe this one is quite common to all of us. So codec refer to the method used to encode and compress the data to enable faster transmission and decompress received data. Okay, so which means the codec is referring to the algorithm in the encoder and decoder algorithm. To encode means to represent the discrete audio sample with the equivalent binary number. So the codec here is to, the codec in the previous chapter, we learned analog to digital conversion, right? So this is continuous, this is discrete data. But in this, in terms of PCM, it is from digital data and convert to binary data, or the bit, so-called the binary 1 and 0 lah. Okay, so please aware of the difference. The codec is not to convert from analog to digital, but digital to binary. Okay, so the codec is meant to represent the discrete data here using binary, which means it is more on this step. Okay, but not A to D. Okay, this is repeated. Uncompressed audio format. Uncompressed audio is exactly what it sounds like, real sound wave that has been captured and converted to digital format without any further processing. So which means this one is just perform uh, analog to digital converter ADC. Okay. As a result, uncompressed audio files tend to be most accurate, but take up lots of disk space, about 34 MB megabyte per minute for 24-bit 96 kilohertz stereo. Okay, so because it is uncompressed, which means no data is being omitted, no matter in lossy or lossless method. So it's should be seen as most accurate lah. But of course, you cannot say that it is exactly exactly the same as per the analog, because during the conversion from analog to digital, it may introduce quantization noise, the some of the noise during introduced into the data when you try to convert from digital analog to digital. Okay, so this audio format do not employ any compression algorithm to make the file smaller, thus it is no loss in quality. So the most popular two uncompressed format would be the WAV and also AIFF. Both are based on PCM, where we learned previously, using very similar technology but slightly changed in data storage. WAV and AIFF both are uncompressed and lossless format. It is lossless because nothing being compressed, so we call it as lossless. Okay, but the best to describe this type of extension would be uncompressed format rather than lossless. Okay, so please are aware, lossless may imply that this information is being compressed but using a lossless algorithm. Okay, but uncompressed format, which means this data is never being compressed, no matter using lossless or lossy compression method. Okay, always aware of this one. So the high quality and simplicity of this file make them easy to edit and process. Thus, they are generally the first choice in professional audio application. Because in the profession, in audio application, we always want the original data, especially when you perform audio processing, for example, for maybe audio recognitions, for voice recognitions. So all these type usually would be uncompressed data lah. Because after you compress the data, perhaps some of the uh, typical features of individual noise would be missing. So it might impinge the overall audio processing algorithm. So WAV, which in short is waveform audio file format, also called audio for window. It is a standard that was developed by Microsoft and IBM back to 1991, suitably to be used on Windows system. AIFF, similar to how Microsoft and IBM developed WAV for Windows, but AIFF was developed by Apple for Mac system back to 1988, so more suitable for use in Mac system. Of course, different manufacturer or different developer, they would have their preferable uh, extension. For example, different OS, they might have different um, some application might need to download with different version, so that the application is compatible to the specific OS. Okay, so this is considered as same level but different OS lah. WAV and IFF considered as same level of applications. Same level of extension format file, but it's applied to different OS. Okay, one is Windows, one is Mac. Remark, nowadays both format can be recorded and playback natively on any operating system, so they are easily interchangeable, offering the same high quality audio regardless of format. Okay, so last time cannot, but now it's okay. So which means you can play some of the audio from Mac, or maybe from Mac, or maybe the Windows OS. Lossy compression audio format. Audio compression format is a content representation format for storage or transmission of digital audio, such as digital televisions, digital radio, and in audio and video file. Mostly audio data compression methods such as Mpeg or audio encoding remove some sound which are masked. So this would be the category where Mpeg is belong to, whereby the Mpeg would tend to remove those data uh, in terms of permanent. Okay, the data which is omitted by Mpeg, no matter Mpeg layer 1, layer 2, or layer 3, all those are removal or omission of data would be permanent. In the context of audio, that means sacrifice audio quality for fidelity for file size. Okay, which means if for some application you have limited bandwidth and you have limited storage and the audio quality is acceptable, reduced to acceptable level, so perhaps you will take this category of extension, for example, the loosely compression data. So the good news is that in most cases, we won't be able to share the difference. This is the main difference because in multimedia, the main, the one who perceives the information is human being. So we have limitation in our auditory system. For example, we cannot hear very, very low frequency or the signal from very, very high frequency. So that is why all the informations within this low frequency and high frequency region are considered redundancy and it's not meaningful to human being. But when you deal with the machine, for example, you want to process it. For example, you want to process it. For professional audio applications, the uh, the one who understand or perceive or decode the message is machine. So machine did not have the same limitation as human auditory system. So that is why for that case, for example, voice recognitions, uh, security purposes. So for this kind of applications, the one who perceive or decode the signal or the tone would be machine. So sort of algorithm. So we cannot apply. We cannot assume that whenever we cannot listen, so the machine cannot listen. So that is why usually we need uncompressed data for audio processing. The same apply to image processing. If let's say you want to process uh, maybe medical images, so all the features in the medical image is important, no matter it is seen or unseen by the human or the expert. So whenever you want to use a specific data for image processing, we always use uncompressed format. Okay, if it is being compressed, although in from the human perspective, there is nothing different before and after the compression, but you have to understand that must be some of the data already lost or already omitted by the algorithm. If not, the size will not be reduced. Okay, so for this one, okay, for the loosey and looseless, usually it is meant for human being. Okay, the interactive main personnel would be the human being. So since we have limitations in terms of auditory system, so it's okay to remove all those redundancy informations and all those signal which is being masked out by the frequency masking or the temporal masking. So if the audio get compressed too much or too often, you will start hear artifact and otherwise weirdness that become more and more noticeable. So it's normal lah. If you compress an image to a very high level, you will be able to see some artifacts in your output image, which is so-called, so because of the blocky field, there will be some artifacts which is introduced by over compression. Okay, the same happens here. If you have over compression, you would hear some artifacts, maybe some sort of noise, which is the result of your, over compression here. Mpeg is a family of encoding standard for digital multimedia information. It relies on quantizations, masking, and critical band. So Mpeg audio conversion take advantages of both temporal and frequency masking, as I already mentioned, to transmit mass frequency component using fewer bit. Example of audio compression include Mpeg layer 1, Mpeg layer 2, which is this ACA MP3 and also AAC. So Mpeg layer 1 is the first time being found is 1991, being proposed, I should use the word, a standard for storage for and retrieval of moving picture and audio and storage media CD-ROM, and layer 1 used for digital audio tape Layer 2 proposed for digital audio broadcasting, and layer 3 would be music lah, meant for normal music, Mpeg layer 3, Mpeg layer 1, layer 3, sorry. So each layer offer more complexity in psychoacoustic model. Always remember, layer 1 we use only frequency masking, layer 2 we use frequency and temporal, and layer 3 we use frequency, temporal, and some other sophisticated filter. And this increase complexity, it lead to increase in delay. Layer 3 adds a DCT, which is a modified DCT, to the subband filter, so that layer 1 and layer 2 work in the temporal and layer 3 in the frequency domain. So these are some of the some of the informations for Mpeg 1, Mpeg 2, and Mpeg 2 AAC. Just for your information. So Mpeg 2 AAC standard for DVD, digital TV and DVD, including high definition television and for addressing multimedia application. Mpeg 4, a standard for multimedia application for fixed and mobile web with very low bitrate audio visual compression for those channels with very limited bandwidth. Mpeg 7, a content representation standard for multimedia content description. Mpeg 1 audio, which is MP3, this is layer 3, quickly exploded in popularity, eventually become the most popular audio format in the world for music file. So MP3 is to cut out all the sound data that exists beyond the hearing range, which is in which it is determined, based on the human being perception, auditory system. So of most normal people, and to reduce the quality of sound that aren't so easy to hear, and then to compress all other audio data as efficiently as possible. Nearly every digital device, such as PC, Mac, Android, everything in the world with audio playback can read and play MP3 file. That is because, as I mentioned before, in digital, in multimedia, we will always prioritize the popularity of a specific extension. For example, JPEG and JPEG 2000. JPEG is much more uh, popular than JPEG 2000, but nonetheless, JPEG 2000 perform better than JPEG. But why? What is the reason why not all the computer readily for you to save the image as JPEG 2000, but instead of JPEG? Okay, instead of JPEG. That is why that is because the JPEG is much more popular among the community and society. So that is why the manufacturer tend to include all these kind of so-called the common file type as the default saving format in your computer. The same goes to MP3. This is the most common file type or the extension used worldwide in term for audio, in particular. So that is why most of the OS different system is able to are able to play back or save the audio in this file format. So AAC is an audio coding standard for loosely digital audio compression. So compression algorithm used by AAC is much more advanced and technical than MP3. It generally have better sound quality, but it's never overtook MP3 as the most popular music for recording. So I would say AAC would have the same destiny as the JPEG 2000, which means, MPEG is like the JPEG, and AAC is like the JPEG 2000. Even though the AAC perform better than MP3, but it still cannot replace MP3 based on due to as the most popular format lah. The encoding efficiency is 30% more than MP3. AAC is widely used today. In fact, it is the standard audio compression method used by YouTube, Android OS, and Okay. So if all these big boss are not going to use the AAC, I don't think AAC, because I don't think AAC will gain its popularity lah. Nonetheless, MP3 is still very very common, I would say, in terms of the layman. Okay, but for this industrial player, especially in audio industrial player, so they really look into the performance instead of popularity, because it's obvious when you compare the quality in details, you will know that one extension is better than another one. Okay, regardless to the popularity. So WMA is a proprietary format created by Microsoft. Therefore, not many device and platforms support it. WMA was meant to address some of the flaw in MP3 compression method, and WMA approach to perform compression is pretty similar to AAC. In some other words, in terms of objective quality, WMA is better than MP3. So it is important to remark that MP3, AAC, and WMA are lossy file format. Okay, but nonetheless, I mean, all these, I mean, it's good for you to know what would be the example in uncompressed file format, compressed, I mean, lossy and lossy file format. But I don't think you need to, memorize what is the difference, what is this? I mean, when is this being introduced? The year? I don't think so. Okay. You can always Google this later on. Okay. Again, I seldom test something which you can Google it. Okay. Of course, there would be some question in that level because to test the knowledge. But again, I don't think it is suitable to, keep on asking something that you can Google later on. Nonetheless, the engineering program is meant to test, I mean, to shape you to become an engineer, but not to shape you to become someone who very good in memorizations, and then eventually later on you don't know. I mean, you will forget everything like if it is not being used in your daily work basis. Okay, so always in engineering, always try to train yourself, I mean, gain the capability to know how to source the answer. Okay, if you gain this kind of skill set, it's easier for you to secure any job, and you can excel in any different field, no matter in engineering, no matter in research, and etc. But of course, the fundamental knowledge you have to know it. But for those that can be, you know, uh, just type and get the answer. You don't need to you don't need to memorize all those things lah. Okay, so lossless compressed audio format, this is lossless, which means no information would be lost at the end. I mean, later on you can decode or uncompress back. This generally refer to file format compress the file but preserving the audio quality, preserving the audio quality of the original file. Free lossless audio codec, which is FLAC, is an open source and royalty-free format rather than a proprietary one. So it doesn't impose any intellectual properties constraint. Proprietary, which means it is belongs to someone else, this which means this application is belong to someone else. If you want to use it, maybe you need to subscribe it to pay and etc. So Apple lossless audio codec ALAC, sometimes referred to as Apple lossless. ALAC is good but slightly less efficient as FLAC when it comes to compression. However, of course, all this extension is not meant for compression alone. You can use it for any other. I mean, you can use this file type for any other uh, audio processing, but not only the compression. Just that in this context, we are talking about the audio compression. However, Apple users don't really have a choice between the two because iTunes and iOS both provide native support for ALAC and no support for FLAC. Okay, so if you are a Mac user, so for sure you have to opt for LAC because I don't think the opt word is suitable because you don't have a choice at all. Typically, FLAC file is around half of the size of this half of the size. This one remove of a WAV or AIFF or equivalence sample rate. The advantage of this file type is that they can convert to any to and from WAV and AIFF with no loss of quality, which means you can convert back. I mean, you can recover the part of data where you are already compressed. Okay, so that is all for the audio processing and audio compressions. As I mentioned, we have two chapters in these portions. I mean, in audio processing. Any questions before we move to another chapter? No. Okay. If you have question, feel free to ask. If you have doubts and etc. Okay. As I mentioned previously, we have 7 chapter in image processing, 2 chapter in audio processing, and 2 chapter for video processing. Um, I would say that audio processing would be the smallest portion, and then followed by video processing and image processing. Because in video processing, most of the processing method applicable to video processing is applicable or is being introduced in image processing syllabus already. Okay, because always remember the video is always a dynamic multimedia whereby you have different static image arranged in the correct sequence and form a so-called video. Okay, this is a time-dependent multimedia or elements, and it is require continuous flow. Require continuous flow of time in terms of time domain in order to understand the message behind the video. Okay. So chapter 10 is about video processing, and chapter 11, which is the last chapter, would be regarding the video compressions. Okay. Mm. I think today I will go for introduction, and then later on, we will officially start this by maybe this Thursday lah. Okay. This Thursday we have tutorial class. So if let's say we've finished the syllabus earlier, we will continue. I mean the lecture sections, the lecture time to complete the tutorial. So after we complete the tutorial, we will. I mean you all can freely propose which chapter that you need to do revision. So we will do revision for that particular chapter. Okay. Uh, I hope you all will propose the chapter that you need revisions. It's because this is online class, and I mean some are hybrid, but nonetheless, I quite worry that um, you all keep silence. Keep everything in silent, and I don't really know if you all understand. So of course, I can know if you understand or not by looking in your assignment and also the lab report. A warm reminder to submit your lab report earlier or before the timeline. Okay, if any late submissions, I will not. I will consider to deduct some of the percentage. Okay. I have clearly mentioned the mark reduction format or the guidelines in the Google Classroom. Please make sure you comply. Okay. Okay. So for video processing, we have analog to digital video, which means no matter for audio or for the video, we always need to convert to digital if you want to process it. Okay. But why we never mention that analog to digital is that um, the images that you snap using your mobile phone or your camera or any other image acquisitions device, it is it is in the form once you snap once you capture the image, the sensor, for example the CMOS sensor in your camera lens will automatically convert it to digital image. So you can view that is why you can view the image with your computer and etc. Another thing is that the image is always in discrete format, which means you don't have a continuous flow of pixel. Instead, you have a discrete value of pixel, for example 0 to 255. Okay, so that is why in image we did not mention analog to digital video, analog to digital conversion. But in audio, yes, you record something else, so-called the sound, and then later on you convert the sound into uh, digital format or so-called audio by using sampling and also the quantization. Okay, so again, in video, we will need to perform analog to digital conversion, and we have different format to display the video. And I believe you all, I mean, after doing the lab, especially your lab report, I think you all have some idea on, progressions, zigzag scanning, uh, some of the basic theory from the some of the basic application or basic algorithm being used in the video processing. Sometimes I would think that I mean you all source for the knowledge first and then learn again from the syllabus or from the lecture. Sometimes I think this so-called the active learning path, I think somewhat is better lah. Okay, so that is why I let you all to do the video processing before the video processing in I mean the lecture for video processing lah. Okay, so yeah, introductions. Video is made of frames and lines, which mean you have different frames arranged in a specific time taken, and for each frame you have line. I think you all roughly know what is the line referring to, where you have scanning from the first line, go to the next, and back to first line, and then zigzag until you finish the entire frame. Okay, this is how the lines be. I mean, this is how the image in the video are being formalized. Actually, it is by line. Okay, so frame per second, we already know these terms in the beginning of this subject. So FPS is the so-called the short form for frame per second or frame rate. Okay, rate is actually referring something per second, okay, or something per hour. It's the number of image occurred in 1 second of time. But in the video, we always measure the frame based on second. Okay, so how many frame in 1 second? So if let's say you have a lot, I mean more than uh, 20 to 40, maybe 50 frame in 1 second, which means in 1 second time, you need to play the 50, let's say 50, 50 frame in the same interval very fast. Okay, so which means you for those video with higher FPS, you would be able, I mean, you would be able to have a higher quality of image. I mean, not a higher quality of video, whereby the movement of the character in the video is very, very smooth. That is because you have, I mean, the each of the frame record uh, the very, very specific or very, very detailed movement of the character. So which means you increase the sensitivity in general lah. Okay. But at the same time, since there are more and more data being covered in 1 second alone, which means your file size would be expected very big lah. Okay. So for example, television broadcasts are usually 30 FPS, movie are 24 FPS, and animation is 12 FPS. So camera with 6 frames per second and camera with 24 frames per second. Let's assume this is 1 second. Oh yeah, I already wrote right here. 1 second. So which means when you have 6 frames in 1 second, which means in 1 second you have six static image or six static graphic here, 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 and here. Okay, showing the continuous movement. Of course, if these six static or these six 24 static images of frame, also called the frame, is not continuous. So obviously your video which I mean you saw some laggy feel over there lah. Okay, like you jumping from one action to another action. So most cameras are capable of frame rates up to 30 fps, but that doesn't necessarily means need that doesn't necessarily mean need to record to at a full 30 fps. This is the I mean, of course not for all lah, but most of the camera has the capability to record up to 30 fps. But of course, you don't really need to record up to 30 fps because this will fix the frame rate. Okay, somewhat you want to record something else with low fps is okay as well. Doing so create redundant data and consume excess bandwidth and storage. Again, in video I mean not only video, audio and image, all the multimedia, we are always considering the bandwidth and also the storage, because we always want to transfer the data from one end to another end, so the bandwidth to transfer required to transfer the data is important and very crucial, and we have limited storage. So that is why uh it's important to have uh I mean, important to weigh up the trade-off between the weigh up the trade-off between the quality of video, image, or audio, and also the storage size. So the average frame rate is security in the security industry fall between 5 fps and 15 fps. So for HDTV you have 60, video you have 60, camera you have 60, mobile 60, 60, and online video you have 30 fps. So important aspect to determine the video quality, which is the frame rate and also motion blur. When a film is recorded at 20 fps, each frame has an exposure time up to 40 milliseconds. Actually, you just 1 divided by 25 lah. Okay. If let's say you have higher, so you 1 divided by the X value. When the frame rate of movie is too slow, human mind will no longer to be convinced that the content of movie are continuous and the movie will appear to jump. Okay, so human again this for video it is again for human being. So the main target is for human. So that is why we always I mean you need to maintain a specific fps. If the fps is too low, for example, uh 3 fps, which mean one frame uh, one frame is around 0.33333 second. Okay, so which mean human eye can I mean able to capture that, oh, why there is a so-called the laggy feel or the jump from one movement to another movement, because human eye can detect. So video data rates are given in a bit per second. So resolution, pixel depth, and the frame rate. So example one, I think we stop here first. I don't want to cover this one. Maybe we will continue by this Thursday. Okay. Any questions before we end? No. Okay. So that's all for today. We will have lecture in I mean on Thursday, and also tutorial on Tuesday as well. Okay. I think I already upload until tutorial 6. You try your best to do the tutorial, and we will discuss. I think tutorial 4 onwards. I think. Okay, I will check back again. From the Google Classroom. Okay, if no questions. So that's all for today, and thank you. Bye bye.